Hey everyone, and welcome back. It's time for another deep dive. And today we're going to be tackling some pretty mind-blowing stuff. We're going to be diving into the world of quantum research.
Quantum research. Sounds exciting.
It is. And we've got an incredible guide for this journey. We'll be exploring an essay by Jürgen Schalapat. It's called Zukunft der Quantenforschung, Visionen und Herausforderungen.
Zukunft der Quantenforschung. Visions and challenges.
Yeah, which basically translates to Future of Quantum Research, Visions and Challenges for our English-speaking audience.
Okay, I see.
So in this deep dive, we're going to unpack how quantum research could revolutionize so many fields. We'll look at the incredible potential and also the challenges we face, and maybe even touch on some mind-boggling ideas like quantum supremacy.
Quantum supremacy.
Like, could quantum computers actually achieve this kind of computational power that surpasses anything we can imagine today?
Now that is a question for the ages.
Right. And Schnappat really gets into it.
Hmm.
But before we get ahead of ourselves, let's take a step back and explore the history of quantum mechanics.
Sounds good. Let's set the stage.
Okay, so imagine it's the early 20th century. Physicists are observing things at the atomic level that just don't make sense according to classical physics.
Right, like the universe is playing by a whole different set of rules down there.
Exactly. And Schnappat highlights this perfectly. He talks about how scientists were struggling to explain these phenomena.
It really was a turning point in physics.
Totally. It was like realizing that our understanding of the universe was incomplete.
Schnappat talks about Max Planck, who was studying black body radiation around the turn of the century.
Black body radiation.
It's basically how objects absorb and emit light.
Okay, I'm following.
So Planck was trying to make sense of this, and he came up with this revolutionary idea. He said that energy isn't this continuous flow, but comes in tiny, discrete packets.
Like little bundles of energy.
Exactly. And he called these packets quanta.
And that discovery just blew everything wide open.
It was a paradigm shift. Suddenly, the old rules didn't apply anymore.
It must have been mind-blowing for scientists at the time.
Oh, absolutely. It was like the universe had revealed a hidden layer of reality.
And Schneepat emphasizes how this discovery by Planck really laid the foundation for the entire field of quantum mechanics.
Right. And then came along giants like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger.
Oh yeah, those are the big names everyone's heard of, even if they don't know much about quantum mechanics.
Exactly. And they took those early quantum ideas and ran with them.
So what did they come up with? Schneepat must dive into their contributions, right?
He does. For example, Heisenberg developed this revolutionary idea called the uncertainty principle.
The uncertainty principle.
Yeah, it's this wild concept that basically says you can never know both the exact position and momentum of a particle at the same time.
So like, the more precisely you know one, the less you know about the other.
Exactly. It's like the universe is putting a fundamental limit on how much we can know about the subatomic world.
That's trippy.
And then there's Schrödinger, who came up with this equation that describes quantum phenomena in terms of waves.
Wait, so we've got particles acting like waves now.
You got it. And this is where the idea of wave-particle duality comes in. It's like light can be both a wave and a particle depending on how you observe it.
Okay, my brain is starting to hurt a little, but in a good way.
It's a lot to take in, that's for sure. But that's the beauty of quantum mechanics. It challenges our everyday intuitions about how reality works.
It's like the universe is telling us, hey, things are way weirder than you thought.
Exactly. And Schneepat does an incredible job of explaining these mind-boggling concepts in a way that's both accessible and thought-provoking.
He makes you want to dive deeper into this quantum rabbit hole.
Definitely.
But here's the thing. Quantum mechanics isn't just some abstract theoretical thing. It's actually impacting our daily lives right now.
Oh, absolutely. Schneepat brings it down to earth by showing how it's already woven into the fabric of our technological world.
Okay, so give us some examples. How is quantum mechanics showing up in our everyday lives?
Well, think about the semiconductors in your smartphone, or the lasers in CD players, or even medical imaging technologies like MRI. All of these rely on principles of quantum mechanics.
Wow, so we're already living in a quantum world in a way.
We are, and it's only going to get more intertwined as quantum research continues to advance.
Okay, so that's the groundwork. We've got this revolutionary theory of quantum mechanics that's already shaping our world in profound ways. But what about the future? This is where things get really exciting, right?
Absolutely. This is where Schneepat's essay really starts to explore the cutting edge of quantum research and the potential for even more mind-blowing applications in the years to come.
Okay, so let's dive into that. What are some of the areas where Schneppat sees quantum research making the biggest impact in the future?
Well, one of the most talked about areas is quantum computing.
Quantum computing. Yeah, I've heard a lot of buzz about that.
It's a hot topic for sure.
But what exactly is quantum computing? And how is it different from the computers we use today?
That's a great question, and Schneppat does a fantastic job of breaking it down. He explains that quantum computers harness the unique properties of quantum mechanics to perform calculations in a completely different way than classical computers.
So, like, they're not just faster versions of our laptops.
No, not at all. They're based on a completely different paradigm.
Okay, I'm intrigued. So, what kind of power are we talking about here?
We're talking about the potential to solve problems in seconds that would take classical computers thousands of years.
Thousands of years.
You heard that right.
That's insane.
It is. It's like comparing a horse and buggy to a spaceship.
Okay, so that's quantum computing in a nutshell.
hmm
But how close are we to actually having these super-powered quantum computers?
Well, that's where things get a little more complicated.
Complicated how?
There are still some major technological hurdles to overcome.
Like what?
Well, one of the biggest challenges is building quantum computers with enough qubits. Yeah, they're like the quantum equivalent of bits in a classical computer, but they're much more delicate and prone to errors.
I see. So it's not just about building a bigger computer. It's about building a computer that can actually harness these finicky quantum properties.
Exactly. And then there's the problem of keeping those qubits stable. They're extremely sensitive to their environment. Even the slightest disturbance can cause them to lose their quantum state.
It sounds like trying to balance a million spinning plates simultaneously.
It's a pretty apt analogy.
Wow. So it sounds like we've got a long way to go before quantum computers are sitting on our desks.
Maybe not on our desks. But in specialized labs and research facilities, that's happening already.
Really?
Yeah, Schneppat even talks about how companies like Google and IBM are already making significant strides in quantum computing research.
I remember reading about Google claiming they achieved quantum supremacy back in 2019.
They did. It was a big deal.
But what exactly did they do, and what does quantum supremacy even mean?
Schneppat gets into that. He explains that Google used their Sycamore processor to perform a calculation that would take in a classical supercomputer an absurdly long time to complete.
So they basically showed that their quantum computer could outperform even the most powerful classical computer on a specific task.
That's the gist of it. But there was some debate about whether the task they chose was truly representative of quantum supremacy.
Debate.
Yeah, IBM argued that Google's claim was a bit overblown. They said that with some clever optimization, a classical computer could actually solve the same problem in a reasonable amount of time.
So the whole idea of quantum supremacy is still a bit fuzzy.
It is, but that's the nature of cutting-edge research. There's always going to be debate and disagreement as we push the boundaries of what's possible.
I guess that's what makes it so exciting.
It is. It's like we're watching history unfold in real time.
Totally. But even if we do reach this quantum supremacy, Schneppat makes it clear that there are still massive hurdles to overcome.
Right. It's not just about building a quantum computer that can outperform a classical computer on one specific task. It's about building a quantum computer that's reliable, scalable, and accessible to a wider range of users.
And that's going to require some serious breakthroughs in areas like error correction, qubit stability, and cryogenics, keeping those qubits super cold.
You're hitting all the key points. It's a massive engineering challenge.
It sounds like it.
It is. But the potential rewards are so enormous that researchers around the world are pushing hard to make it happen.
I, for one, am eager to see what the future holds for quantum computing. It sounds like it could revolutionize everything from medicine to material science to artificial intelligence.
It really could. And Schneppat's essay gives us a glimpse into those possibilities.
Okay, so we've talked about quantum computers and the race to achieve quantum supremacy. What other mind-blowing quantum technologies does Schneppat explore?
Well, he dives into this fascinating world of quantum sensing.
Quantum sensing?
Yeah, it's all about using the unique properties of quantum systems to make incredibly precise measurements.
You mentioned something about detecting a butterfly flapping its wings a mile away.
I did. That's a bit of an exaggeration. But it captures the essence of what quantum sensing is all about. We're talking about measuring things with a level of sensitivity that was unimaginable just a few decades ago.
So how does this work? What are some examples of quantum sensing in action?
Schneppat highlights a few examples, like using quantum sensors to detect minute changes in magnetic fields. This has huge implications for medical imaging. Think MRI scans, but with even greater resolution and sensitivity.
So we could be using quantum sensors to diagnose diseases earlier and with more accuracy.
Exactly, and that's just the tip of the iceberg. Quantum sensors could also be used to detect gravitational waves, those ripples in space-time caused by massive events like black holes colliding.
It's like listening to the heartbeat of the universe.
It is. And Schneppet even talks about using quantum sensors to probe the fundamental structure of matter itself.
Okay, my mind is officially blown. Quantum computers, quantum sensing. It's like we're stepping into a science fiction novel.
It does feel that way sometimes, doesn't it?
It does. But what's really amazing is that this is all happening right now. It's not some distant future. This is the cutting edge of science unfolding before our very eyes.
And Schneppat's essay does a fantastic job of capturing that sense of wonder and excitement.
He really does. Okay, so we've got quantum computers and quantum sensing. What other mind-blowing applications does Schneppet have in store for us?
Well, buckle up, because we're about to enter the world of quantum cryptography.
Quantum cryptography. Sounds intense.
It is. It's all about using quantum mechanics to create encryption methods that are virtually unbreakable.
Unbreakable.
Well, theoretically unbreakable.
So, like, we could finally say goodbye to those pesky hackers.
It's certainly a possibility, but as with everything in quantum mechanics, it's a bit more complicated than that.
Okay, so break it down for me. How does quantum cryptography actually work?
Schneppet explains this really well. It all comes down to a concept called quantum key distribution, or QKD for short.
QKD.
Yep.
And what is QKD exactly?
It's a way of using quantum particles like photons to create encryption keys that are impossible to intercept without being detected.
Okay, so if someone tries to eavesdrop on a communication that's protected by QKD, they'll immediately be caught red-handed.
Exactly. The very act of trying to intercept the key would alter its quantum state, alerting the sender and receiver that something's fishy.
So it's like having a built-in alarm system for your data.
You got it.
That's pretty amazing.
It is, and it has the potential to revolutionize cybersecurity as we know it.
So does this mean we can finally kiss those data breaches and identity thefts goodbye?
Well, Schneppat is a bit more cautious about making those kinds of sweeping claims.
Why is that?
He points out that while QKD is incredibly promising, there are still some practical challenges to overcome.
Like what?
Well, one of the biggest challenges is scaling up QKD to work over long distances and across complex networks.
Right, so it's one thing to secure communication between 2 points, but it's another thing entirely to secure the entire internet.
Exactly. And then there are concerns about the cost and complexity of implementing QKD infrastructure.
So it sounds like we're still in the early stages of quantum cryptography.
We are, but the potential is there. And Schneppat's essay makes a compelling case for why we should be investing in this technology.
Well, I, for one, am excited to see how this all plays out. Quantum computing, quantum sensing, quantum cryptography. It feels like we're on the verge of a technological revolution unlike anything we've ever seen before.
I agree. And Schneppat's essay does a fantastic job of guiding us through this complex and fascinating landscape.
He really does. Okay, so we've covered a lot of ground so far. We've explored the history of quantum mechanics, the mind-bending concepts that underpin this field, and some of the most promising technological applications. But Schneppet doesn't stop there. He also takes us on a journey into the philosophical and ethical implications of quantum research. And that's where we're headed next.
Buckle up, it's going to be a wild ride.
I can't wait.
It's really amazing how Schneppet brings those historical figures to life in his essay. You know, it's easy to get lost in the equations and the abstract concepts, but he reminds us that these were real people with their own passions and rivalries.
Yeah, he paints such a vivid picture of those early pioneers of quantum mechanics. You know, like they were grappling with these mind-boggling ideas and trying to make sense of a universe that was suddenly a lot weirder than they thought it was.
Exactly. He talks about how Max Planck, while studying black body radiation, you know, that's how objects absorb and emit light.
Right.
He stumbled upon this revolutionary idea that energy isn't this continuous flow, but it exists in these discrete packets, which he called quanta.
So it's like energy comes in these tiny little bundles.
Exactly, and that was a radical idea at the time. It completely challenged the prevailing view of physics.
Yeah, it must have been like, whoa, hold on, what's going on here?
It was a huge paradigm shift, and from there, things just kept getting weirder.
Weirder in a good way, I hope.
Oh, absolutely. Schneppet then brings in Einstein, who, building on Planck's work, explained the photoelectric effect.
The photoelectric effect. Remind me what that is again.
It's basically how light can knock electrons loose from atoms. It's another piece of the puzzle that showed light could act like a particle as well as a wave.
Ah, okay, so it's like light has this dual nature. It can be both a wave and a particle depending on how you're looking at it.
Precisely. It's one of those mind-bending concepts that makes quantum mechanics so fascinating and challenging.
I'm starting to see why those early quantum physicists had so many heated debates.
Oh yeah, Schnepp even mentions how Niels Bohr, who developed a model of the atom that incorporated these quantum ideas,
Yeah, Bohr's model.
it sparked all sorts of arguments and disagreements within the physics community.
It sounds like the quantum world was a pretty dramatic place back then.
It was. Schnepp talks about how Werner Heisenberg and Erwin Schrödinger, two of the giants of quantum mechanics, had very different approaches to understanding this strange new reality.
Okay, so Heisenberg and Schrödinger, what were their big ideas?
Well, Heisenberg developed this revolutionary idea called the uncertainty principle.
Ah, yes, the uncertainty principle. One of those things you hear about even if you don't really understand it.
It's basically the idea that you can't know both the exact position and momentum of a particle at the same time.
So it's like the more precisely you know one, the less you know about the other.
You got it. It's
Yeah.
like there's this fundamental limit to how much we can know about the subatomic world.
It makes you wonder if reality is even knowable in the way we traditionally think about it.
That's a deep philosophical question that Schnepp touches on as well.
We'll have to explore that more later. But for
Mm.
now, back to Heisenberg and Schrödinger.
Right. So while Heisenberg was focused on these abstract mathematical representations called matrices,
Matrices.
yeah, they're these grids of numbers that help describe quantum phenomena.
Ah, okay.
Schrödinger came up with this equation that described quantum phenomena in terms of waves.
So we got particles, matrices, waves. It's a lot to keep track of.
It is. But the amazing thing is that despite their very different approaches, both Heisenberg and Schrödinger contributed enormously to our understanding of quantum mechanics.
So it's like they were looking at the same elephant from different angles,
Hmm.
but they were both right in their own way.
That's a great analogy. And Schnepp goes on to highlight the contributions of so many other brilliant minds who shaped the field.
It's like a whole constellation of quantum stars.
Exactly. And it wasn't just those early pioneers. Schnepp also mentions contemporary leaders in the field like John Preskill, Michelle Simmons, John Weipan.
Okay, so these are the folks who are pushing the boundaries of quantum research today.
They are. Preskill's work in quantum information theory, Simmons's research on silicon-based quantum computers, Pan's groundbreaking experiments in quantum communication and cryptography.
These are the rock stars of the quantum world.
They are indeed, and their work is building on the foundations laid by those who came before them.
It's inspiring to think about all these brilliant minds working on this stuff right now.
Yeah.
It really feels like we're in the midst of a scientific revolution.
We are, and Schnepp captures that sense of excitement and possibility in his essay.
Okay, so we've talked a lot about the people behind quantum research, but let's circle back to some of the key concepts Schnepp outlines. He spends a lot of time unpacking this idea of quantum supremacy, right?
He does, and it's a concept that captures the imagination.
Yeah, I remember we touched on it earlier, but let's dive a little deeper.
Okay, so remember, quantum supremacy is this idea that a quantum computer can solve a problem that's practically impossible for even the most powerful classical computer to handle in any reasonable amount of time.
Yeah, it's like a computer on steroids.
It's like having a super-powered calculator that can crack codes, simulate complex molecules, design new materials, all sorts of things that would take classical computers centuries to figure out.
I know Schnepp had mentioned Google's claim of achieving quantum supremacy back in 2019. Did he go into any more detail about that?
He did. He explains how Google used their Sycamore processor to sample the output of a random quantum circuit.
Random quantum circuit.
Yeah, it's basically a way of testing a quantum computer's capabilities.
Okay.
And they showed that their Sycamore processor could do this in a matter of minutes, whereas it would have taken a classical supercomputer an absurdly long time, like tens of thousands of years.
So they basically proved that their quantum computer could outperform even the most powerful classical computer on this specific task.
That was their claim, but as you might remember, there was some controversy surrounding it.
Right, IBM wasn't too happy about it, were they?
They weren't. Schnepp presents IBM's counter-argument, which suggested that Google's problem wasn't quite as insurmountable for classical computers as they initially claimed.
So it's like a scientific duel with these tech giants battling it out for quantum supremacy.
It kind of is, and it highlights how the field is still evolving, and there's a lot of debate about what constitutes true quantum supremacy.
It's like we're in this wild west of quantum computing, with everyone staking their claims.
That's a great way to put it. And Schnepp emphasizes that regardless of who won this particular debate, the progress in quantum computing is undeniable.
Yeah, it feels like we're on the cusp of something truly revolutionary.
We are. But even with all this progress, Schneepat reminds us that there are still some major hurdles to overcome.
Like what?
Well, for one thing, building quantum computers with enough qubits and keeping those qubits stable is incredibly challenging.
It's like trying to herd cats, right?
It kind of is. And then there's the problem of error correction in these complex quantum systems. A single error can cascade and corrupt the entire computation.
So it's not just about building a quantum computer that's powerful. It also has to be incredibly precise and reliable.
Exactly. It's a massive engineering challenge, but the potential rewards are so great that researchers around the world are pushing hard to make it happen.
It's exciting to think about all the possibilities that quantum computing could unlock.
It is. And quantum computers aren't the only game in town. Schneepat also dives into this amazing world of quantum sensing.
Ah, yes, quantum sensing, the one where we can detect butterflies flapping their wings a mile away.
Well, not quite, but it's still pretty incredible.
Okay, so remind me again, how does quantum sensing actually work?
It's all about harnessing the unique properties of quantum systems to make incredibly precise measurements.
So, like, what kind of measurements are we talking about?
Well, Schneepat gives a few examples, like using quantum sensors to detect minute changes in magnetic fields, which has huge implications for things like medical imaging.
Yeah, you mentioned earlier that it could lead to more sensitive and accurate MRI scans.
Exactly. And there are other potential applications as well, like using quantum sensors to detect gravitational waves.
Gravitational waves, those ripples in space-time caused by massive objects like black holes.
The very same. It's like being able to listen to the universe itself.
That's mind-blowing. What about using quantum sensors to probe the fundamental structure of matter?
Schneepat touches on that too. It's like having a quantum microscope that can see things at an atomic level.
It's amazing to think about all the things we could learn about the universe with this kind of technology.
It is. Quantum sensing is a rapidly evolving field with incredible potential in areas like medicine materials, science navigation, and even fundamental physics.
Okay, so we've got quantum computers that can crunch numbers like nobody's business,
Yeah.
and quantum sensors that can measure things with mind-boggling precision. What else is on the quantum menu?
Well, how about some quantum cryptography to spice things up?
Quantum cryptography. Isn't that the one that's supposed to make our online data unhackable?
It is. Schneepat dives into this fascinating world of quantum key distribution, or QKD as it's known.
QKD.
Yep.
So remind me again, how does QKD work?
It relies on the fact that measuring a quantum system inevitably disturbs its state.
Okay.
So if someone tries to intercept a key that's been encoded in quantum particles, they'll leave detectable traces.
So it's like a tamper-proof seal on your data.
You got it. Anyone trying to eavesdrop would immediately set off alarm bells.
That sounds pretty foolproof.
It's incredibly secure, but Schneepat is careful to point out that QKD isn't a silver bullet.
What do you mean?
Well, for one thing, implementing QKD on a large scale is a huge technological challenge.
Right, it's one thing to secure communication between 2 points, but it's another thing entirely to secure the entire internet.
Exactly. And then there are concerns about the cost and complexity of QKD infrastructure.
So it sounds like we're still in the early stages of quantum cryptography.
We are, but the potential is there, and Schneepat makes a compelling case for why we should be investing in this technology.
It's like we're witnessing the birth of a new era of cybersecurity.
It is, and it all comes back to those fundamental principles of quantum mechanics that we were talking about earlier.
It's amazing how this one theory has given rise to so many incredible technologies and possibilities.
It really is. And Schneepat's essay does a fantastic job of weaving together the science, the history, the philosophy, the potential, and the challenges of quantum research.
He's given us a lot to think about.
He has. But we're not done yet. Schneepat doesn't just explore the scientific and technological aspects of quantum research. He also dives into the philosophical and ethical implications of this field.
Okay, so we're going even deeper down the quantum rabbit hole.
We are. And that's where we're headed next.
All right, so we've explored this incredible science behind quantum research, and we even dipped our toes into those mind-bending theories, the ones that make you question the nature of reality itself. But Schneepat doesn't leave us hanging in some abstract cosmic void. He brings it all back down to Earth by exploring those very real-world impacts of these quantum leaps.
Yeah, you're right. He constantly reminds us that this isn't just about equations and theories. It's about how this quantum revolution could actually reshape our lives, our society, and even our future.
Totally. It's like we're standing on the edge of this, uncharted territory, and Schneepat is our guide. right? He's pointing out both the breathtaking vistas and the potential pitfalls that we might encounter along the way.
He does a great job of that. And one of the most immediate impacts he highlights is the potential for quantum computers to just completely disrupt cybersecurity as we know it.
Oh yeah, I remember reading about that. It's kind of scary to think that all those encryption algorithms we rely on to protect our online data could become obsolete overnight.
Yeah, it's a real concern, and Schneppat really dives into explaining how some of the most widely used encryption methods today rely on mathematical problems that are difficult for classical computers to solve, but they could be cracked wide open by a powerful enough quantum computer.
So basically all our online banking, our shopping, our communications, everything could be vulnerable.
It's a possibility, and Schneppat emphasizes that governments, businesses, and cybersecurity experts are already working on developing new encryption methods that are resistant to these quantum attacks. It's a race against time to stay ahead of the curve.
It's like a real-life cyberpunk thriller playing out in front of us.
It kind of is, and the stakes are incredibly high.
Yeah.
But cybersecurity isn't the only area Schneppat addresses. He also talks about how quantum technologies could revolutionize medicine materials, science, and even energy production.
So it's not all doom and gloom.
Definitely not. Schneppat is actually quite optimistic about the potential for quantum research to solve some of humanity's biggest challenges.
Okay, so give us some examples. What are some of the positive impacts he highlights?
Well, he talks about how quantum simulations could be used to design new drugs and materials with unprecedented precision. Imagine being able to create materials with specific properties like superconductivity or extreme durability, all thanks to a deeper understanding of the quantum world.
It's like we could be on the verge of a material science revolution.
Exactly. And Schneppat also explores how quantum principles could lead to more efficient solar cells, new types of batteries, and even the possibility of harnessing nuclear fusion, the same process that powers the sun.
Wow. So we could be talking about a future with clean, abundant energy thanks to quantum research.
It's a possibility, and it's one that Schneppat is clearly excited about.
I have to admit, I'm getting pretty excited too.
Mm.
But I know Schneppat also dives into some of the potential downsides of this quantum leap. What are some of the concerns he raises?
Well, he's very thoughtful about this, and one of the key issues he addresses is the potential for job displacement. As quantum computers become more powerful, they could automate tasks that are currently performed by humans, leading to job losses in various sectors.
That's a valid concern. It's important to think about the societal impact of these technological advancements
Hmm.
and to ensure that the benefits are shared widely and that we don't leave people behind.
Absolutely. And Schneppat emphasizes that we need to have open and honest conversations about the ethical implications of quantum research. How do we ensure these powerful technologies are used for good and not for harm? How do we prevent them from exacerbating existing inequalities? These are questions we can't afford to ignore.
It's like Spider-Man's Uncle Ben said, with great power comes great responsibility.
Exactly. And Schneppat's essay is a call to action. He's urging scientists, policymakers, and society as a whole to engage in a thoughtful and informed dialogue about the potential benefits and risks of quantum research.
So he's not just presenting the science, he's also challenging us to think about the bigger picture and to consider the ethical implications of what we're creating.
Exactly. He's saying, hey, we've stumbled upon this incredibly powerful force, and now it's up to us to figure out how to use it for the betterment of humanity.
That's a powerful message. And it brings us to the end of our deep dive into Jurgo Schneppat's Future of Quantum Research, Visions and Challenges.
It's been quite a journey from the mind-bending weirdness of quantum mechanics to the very real-world implications of this rapidly advancing field.
We've covered a lot of ground, and I hope our listeners have come away with a deeper appreciation for both the incredible potential and the complex challenges that lie ahead.
I'm sure they have, and I hope it's sparked a curiosity to learn more about this incredible field that's reshaping our understanding of the universe and our place within it.
Absolutely. Quantum research is still in its early stages, and who knows what amazing discoveries and applications lie just beyond the horizon. It's an exciting time to be alive and to witness this quantum revolution unfold.
I couldn't agree more. It's a time of both great promise and great responsibility.
Well said. And on that note, we'll wrap up this episode of The Deep Dive. Thanks for joining us on this exploration of quantum research. We'll be back soon with more deep dives into the ideas and discoveries shaping our world. Until then, stay curious.